Alright, so what I want to do in this video is find the equation for the tangent and normal line at the function that function. And it's like a product and a quotient. It looks like it's a lot, and we want to do it at x equals 1. So the reason why I want to do this problem is because we spend a lot of time in class or like calculus classes taking derivatives of random functions and just doing that over and over and over again. But we sometimes don't see what the purpose or the interpretation of the derivative is. So I want to show you the interpretation of the derivative in case you don't remember it, right? So let's say I have this random curve and it's f of x, right? And then I have this is the x-axis. Let's say I wanted to find the derivative at, let's say here, a, right? X equals a. So that means its point here is f of a. So that's about right here, f of a. What the derivative does is that it measures the rate of change or the slope, if you want to think of it like that. Let me draw that a little bit better. It draws the tangent line one more time. The tangent line, I guess that's fine. The tangent line to the point, tangent line at that point to the curve, right? So this is a tangent line to this curve at this point, right? This is what we call the derivative at a, or f prime of a. So this is what we want to do with this problem, but the function definitely does not look like this. It looks like something else, and we'll see what it looks like at the end when we get our answer. So purple pen, let's do it in purple. So I want to find the derivative of this function, and it's a product and it's a quotient, and then there's adding. So when I see this, I see it broken down into two parts. I have the product, and then I have this quotient looking thing right here. So let's do that. The derivative of f of x is equal to, right, whatever we have to use the product rule, and then maybe the quotient rule, maybe something else, I don't know. Let's look at it later. So let's do the product, right? So let's do the product, the first part, the product. So x squared minus 1, x squared minus 2. When we do the product rule, we should know which one's the first one and which one's the second factor, right? So this is x squared, and then this is x squared minus 2, and then the derivatives are 2x, and then g prime is also 2x. And we just fit it into the formula, right? So f prime of g is f and g prime, when you multiply them together, is, remember that it is f prime of g plus f g prime, right? So we want to just plug that in straight into, since we have all the information. So 2x is f prime. G, we have to keep the same, 2x squared minus 2, plus, we want to keep f the same now, and then g prime is also 2x. So we can simplify this further if you want. We don't really need to. We're fine at the moment. So now let's look at the second part, right? The second part I'll do right here. We have this function, or this term, and I kind of don't really want to use the quotient rule, right? The quotient rule is too much work. Sometimes, actually most of the times, you can avoid using the quotient rule by rewriting it somehow. In this particular case, we can rewrite it as x squared over x plus 3 over x, right? It has a common denominator of x, so we can kind of like split it into two terms. And this is so much easier to find the derivative of, right? Let me just write it a little, let's just further simplify. This is x, and then let's write it like this. Maybe this might be better. So now what's the derivative of that, right? Derivative of x plus 3x to the minus 1. We have to use the power rule. That's just 1 plus, and then you bring down the minus 1 sign over, 3, minus sign over. So negative 1 times 3x, and then negative 1 minus 1, subtract 1, you get minus 2. In other words, it's just 1 minus 3 over x squared, right? So we have what the formula of the derivative is. I'm going to write it, I'm going to move this here actually, since we have space here. Derivative of x is precisely 2x, x squared minus 2, plus x squared minus 1, 2x, and then we want to add that part, plus 1 minus 3 over x squared. Let me just show you that these are different from each other. Right, so I'm going to zoom into this part, and I'm also going to write what the function is, just to remind us. So we can find a derivative of functions that look really weird. It's kind of what this problem is looking at. So here, let's zoom into this part. Oh, too much. There we go. Let's do it like this, right? So what I want to do now is find the slope, right? Find the slope at x equals 1. That's kind of like finding the tangent line slope, right? Remember that interpretation we had before. Find the slope at 1. Well, this one is the slope formula if you want to think of it like that. So if I plug in 1 here, it should give me the slope, which is 2. I'm going to go through this just plugging in, right? Just plug in 1 to all these terms. You get, what, 1 minus 2, that's negative 1, plus, say 1, this is 0, and then this is 2, 1 minus 3. And then this goes away, so this is just minus 2 plus 1 minus 3, which is equal to, what is this? Minus 1 minus 4. Minus 4. And this is the slope. We have a component of our equation of the line, right? We have a slope. What else do we need? We need a point, right? Point slope. Point slope. How do we find the point? Well, we could actually find the point just by looking at the original function and plugging in that same value. And this is what you have to do to find the point. You have to use the same value to the original function, and then you have to use that value in the derivative function. So let's do that. If I plug in 1, I get, oops, let me just go back down. I don't know why I did that. There we go. So we just plug in 1. So, oops, let's go a little bit up higher. You can see what the original function is. There we go. So you just plug in 1 here. 1 minus 1, that's 0, and then 1 minus 2, and then what is this? 1 plus 3 over 1. And then this is 0, so this whole thing goes away, and this is just 4. Right? So we see we have two important things. The slope and then the point, right? The point is, if we plug in 1, we get 4. So now we can write the equation of the tangent line at the point x equals 1, or at x equals 1, right? So remember that the point slope formula looks like this. There we go. So now we just, so let's see, 4, and then the slope is minus 4. It should be an equal sign. X minus 1. And we're basically done here. If you really want, we can simplify this further and bring it to y equals, and that's fine too, but usually doing a lot of work is just, you might make a mistake, right? You might just make a mistake and it's too much. If you're just not careful, you would make a mistake converting it to a slope intercept. So this is the tangent line. Tangent line. Not too bad. Okay. So what is the normal line, right? How do we find the normal line from the tangent line? We can actually, right? I think the way I was taught it is that you look at the slope, 4, negative 4. What you want to do is find the opposite reciprocal of that number. Opposite reciprocal. What does that mean? It means just flip the sign, right? Flip sign and flip fraction. Flip the sign and flip the fraction. So the way we do it to negative 4 is we flip it to positive 4, and then we flip this fraction to 1 over 4, right? Flip it. Like pretend this is over 1, and then you just flip it. If it was a fraction, you would just flip the fraction and whatever that is. That's the normal slope. So let's do that. Y minus 4 is equal to 1 over 4 x minus 1. This is the normal line, and we are done with this problem. Let's look at the graph to see if we were correct and what it looks like. Alright, so here I have the graph, and I'll zoom out so you can see the graph in its entirety. It looks really odd, right? You have like this thing that comes down, it goes from positive infinity quickly to negative infinity, and then it appears there's nothing at 0, so then it comes back from infinity and it has this parabola looking shape. It's a very odd function, but we're looking specifically at what point are we looking at? We're looking at x equals 1, right? So here's x equals 1 right here. Let me see if I can zoom it in a little bit more. That's a bit too much. Let's do a little bit out. Now let's just keep it like this. So I'm just going to bring it up. So here's x equals 1. It seems like it's right here, right? At the point 1, 4, right? Right there. What we want to do is we found the equation of a tangent line and we found a normal line. So let's see if that is. So I have it here. This is the tangent line, this green line. So if we look at it, it looks like it does touch exactly at one point, right? If I were to zoom in, you can see that point where the black dot is. It just seems to touch it barely, right? If we zoom in, it'll just keep on going like that forever. But we're also focused at the normal line, which is this purple line. See that by taking the negative or the opposite reciprocal, it makes a right angle, right? Right angle right here, right? It's normal to this line, it's normal to the curve at the point. So just remember that this is kind of what derivatives are usually used for, finding slopes of tangent lines, and we'll see other applications of derivatives in future sections, but this is the main one we should be focusing on, especially when introducing derivatives. So that's it.